5. Um, that's why I started to rotate. I didn't see. I think which one now. Okay. Go full screen. Okay. So the law there was, I'll give you a quick example, even though it's calculus and something Tomas asked me before class. And so if you have, for instance, sorry, and thank you, 1 plus, and that's a very simple case, 1 plus 1 over whatever. So what you can do is say, we learned what is 1 plus 1 over 2n in the power of 2n, meaning when this tends to 0, and this is its direct inverse, that's the rule we did learn, you know that this goes to e, right? But it does not actually equal that, right? Because I added a 2, that's a wouldn't it be nice? So then you fix it by taking the power of the half. So the limit is e to the power of half. Okay, so that we did learn. I like I said, I've given a shorthand way to solve this kind of question that I didn't show you in class, but I will show you when we come to functions later on. Okay, and in general, let's. Do you care, Thomas? You're like the most you have the best attendance. Do you wish to fix some date when you can come and ask everyone are invited? But I'm fixing with you because you will surely come to ask questions about homeworks and the class and whatnot.
I mean, we can, and this week is the worst, but when are you free to do it?
When are you? Okay, for example, next Tuesday before class.
Next Tuesday. Ah, yeah, sure.
Yeah, so let's say 11 at my office.
The thing is that the Ulpan
guys.
Ulpan. No,
there's no Ulpan on Tuesday.
Sure, then yeah.
Yeah,
I have an interview with the army, so
you have to with the army. I'm sorry.
Okay, so everyone is invited. I'll tell you. First of all, let me. It's the 20th.
Thursday after I have your mummy.
Kabbalah באנגלית, so I'll write it on the board. Whoever wants to come, I'll tell you exactly when and where. But then we can make sure that everything is in order, or it's not in order, and how to order it. Okay, so not save. Let's do linear algebra, and I write there the short Kabbalah office hours. And remind me in calculus, I'll say it again because of the couple of students comes there and does not come here. Okay. Which lecture are we at? Anyone know?
Great question. I can check in YouTube and see how many we've done. I think
I'm not writing.
5. But that's
that's too low.
That's again.
It's 5, no?
No, it's not
Week 6.
There was
we're at week 8. So
What?
So maybe
You're joking.
maybe we missed a few week 8 of the semester. So maybe we missed a few lessons for once I was abroad. Maybe there were holidays, but in general, it's like the 8th week of
it's probably
the
6,
semester.
but I can check it.
Yeah, I don't write it. Whatever. Forget it.
It's just a flow of conscience next.
Okay, shit. In any case, next week at 20 of May of 25, we'll have office hours at 11 to until the class, basically, at my office, which is not far at all, and math building and 216 right there, and at the upper floor, office number 206. Okay, so let's start with that. If you find it helpful, we can do more office hours. I will be glad to help you. I'm
Yeah,
like I always say, I'm very worried that most people do not come to class. I'm not sure what they're supposed that will happen. And we'll see if it's many things or just small things, and then I'm not worried. Both examples you showed me, I'm not too worried
no,
about,
it's just that.
because I also know what I taught you.
Yeah, no, I was just looking at the other people's homeworks from other classes, and they're by the sixth homework, and we're at the fourth. So I'm like, okay, did we miss something? Did we skip something? Like, what's going on?
We're learning a bit slower than the Hebrew class, obviously, right? But that's good for you guys. And also, I gave you myself homeworks to do, I think in both classes, like question number 5 in calculus. In calculus, we talked about the test last time, and in linear algebra, I gave you the solving a system of equations with parameters. So that will prepare you for the test, which is arguably an important task. Sorry. Okay. And when is the quiz?
The 22nd, I
There's
think.
one next Thursday,
Yeah, which is which?
and there's another Thursday after.
We don't know which one is which, but we have one on the 22nd and one on the 29th. I think 22nd is calc and the 29th is linear algebra.
Okay.
Don't quote me on that.
Okay.
You know which is which?
Okay, I talked to Neil. בסדר. Fine, so that's that. Now, we are in vector spaces at the introduction part. So I asked, what is a vector? And geometrical or physical, it's a magnitude and a direction. Did I not copy? I did show you Newton's version, right? But I didn't copy it onto the board. Do you remember I showed you how Newton did it, right? So, okay. So the summation, the addition of two vectors is the diagonal of the parallelogram between that is created by the two vectors, that geometrically. And algebraically, it's simply 1 plus 5, 2 plus 3, right? Much easier. And another operation we wish to do with the vectors is multiplication by a scalar. What is 2 times the vector 2, 5? So algebraically, what is the answer here?
410.
410, right? Algebraically, it's easy. Geometrically, continue introduction and to vector space. Okay. So geometrically, what does multiplying by 2 does?
Sum it with itself.
That's not geometrical.
It
It's true, but it's
it
not.
enlarges it by the point equal to origin.
Yeah. Multiplying by 2 enlarge the magnitude, whatever it means, by a factor of 2. So like I said, vectors have their let's show you it for I'm guessing you can imagine it, but still I'll do it. Vector 2, 5 it was, right? Two, 5. And 2 times the vector is simply a longer vector, right? 2 times the length, agreed? So that's the geometrical interpretation of multiplying by a scalar over the real field. If the scalars were complex numbers, then it won't be as clear as to what happens when you multiply by 1 plus I, right? But that's kind of my point. As usual, we have 2 windows into the subject, the geometric and the algebraic. And we are in the course algebraic, linear algebra. We're in an algebraic course. So the way we'll look at it will be mostly algebraic, but for every now and again, I will give you a visualization of the problem so you can imagine it geometrically. It does help, but all of the theory and the way we solve exercises will be mostly algebraic. So we are in linear algebra, and we will focus on the operation and their properties. And that will be the definition in a few. Before we continue to the exact, accurate, I think it's better, the accurate definitions, some more introduction. So why do I just continue? Why do I tell you more introduction? Because it's 2 kinds of introduction. And up until now, it's an introduction that you use all the time. I don't know if all the time, but often. You visualize how it looks geometrically, and you understand what it means algebraically. And all the time we'll do it, every now and again. The next part of the introduction is a step forward as to how do we use it in other cases. You will see. But the story behind it goes as follows. We have geometry. We describe it by algebra. So we have the geometry. We describe this geometry by algebra. What is the profits here? What did we gain here? We can solve geometric problems using the algebra quite easily. Like we saw, the addition of vectors is much easier algebraically, the multiplication by a scalar, but many other things. Even if I ask you what is the angle between 2 vectors, just look at it for a second. You don't even have to write it. What is the angle between 1, 2, 3 and 4, 5, 6? How can I find the angle between these 2 vectors? You don't know, and it's fine. That's true, by the way. We dot product. But that's a linear algebra too, exactly. Using the dot product. Hi. So so this is just an example I really like, because if you try to think of it geometrically, it seems, how the hell am I supposed to find the angle between 2 vectors in a 3-dimensional space? I have no idea what's going on, right? The meme of it's an old meme of a dog in a lab. And so, but algebraically, it's so easy using dot product. It's the cosine of the angle is the dot product divided by the product of the lengths of the vectors. It's not even in this course. It will be in linear algebra too. But I really like this example as to something that geometrically it looks very hard, but practically algebraically is very easy. Okay, so so we have geometry. We describe this by algebra, but the next step, yes,
Also-
Sammy.
Surely all you would have to do. Oh wait, hang on, because it's 3D.
Yeah,
Okay, no.
that's the thing.
I was gonna say all you have to do is like find the triangle.
Exactly. That's why I gave you 3D and not 2D, because in 2D it's easy. You can find the angles using trigonometry. But here, the thing is, the two vectors in the 3D space, they create a plane. But it's very hard for you to work within that plane.
Which is why you need the dot product.
Yeah, it's not the only reason for the dot product.
The
Yeah.
dot product is like
Yeah.
the perpendicular to the plane. Was that the cross product? That's
Oh, yeah, that's a cross product.
No.
That's something else. But in any case, that's linear algebra too, to be honest. The dot product, cross product, I don't think you do in linear algebra at all. Dot product will be in linear algebra too. But I do have other examples that we will see that we solve geometrical problems algebraically. I just wanted to give you a quick one so you have it in your head. Because we have problem in geometry and we use algebra to help us with the geometry. So the focus is still on geometry. The next step, and I think this step will be most of what we do in the course. We look algebraically at the geometrical problems. But the next step that doesn't happen within the course, but does happen in the wild, is how can I phrase it? Finding this algebraic structure at non-geometric problems. So the geometry was one thing, we describe it by algebra, and then we say, but this problem has nothing to do with geometry, but algebraically, it looks just like vectors. So we can use all the tools we build for vectors with that problem, okay? And I will give you a specific example for it. For example, functions in general could be seen as vectors. You can sum them up and multiply by scalars. So, but what does it mean that it's vector? Does a function has a direction and a magnitude? Not really clear, right? But still interesting stuff does occur and specifically sound wave trigonometric functions, and I will give you an example. When I whistle in a second, the computer will record my voice. What is a voice? It's a change in air pressure. Do you agree? The program with this is Adobe Audition. It's not a mathematical software. It's for analyzing and editing, more than editing than analyzing audio. The software will show you a graph of the air pressure. So when I whistle, how do you suppose the graph of the air pressure will look like?
unique form in the sense that the highs and the lows will be the same.
But show me with your hand, what would it? Yeah, it would be a sine. So this looks like shawarma. You zoom in and you actually see a kind of a sine function and free-range sine functions, meaning that I created it with my mouse, basically, not with computer software. What are the changes between the different whistles? I won't go too far into it because it's not the main thing here, but it is interesting. This is the first whistle. We see 1, 2, 3, 4 heights. The second whistle has 1, 2, 3, 4, 5 and a bit heights, which is the frequency, which is what we hear as the note. How high it is, that's the amplitude, that's the how loud, the loudness of the voice. And the third one was had a low frequency and a low amplitude. So we can hardly even see it, but now you can. It was less than 3 times at that specific random time frame. Yeah. And so these are the notes. Now, can any of you whistle? Come, Sammy, please.
Wait, hang on, let me stick them out. But,
Yeah. Okay. So when I tell you, then whistle. Thank you, Sammy. Okay. And you look at my point now. Let's again zoom in and see what we see. What does it look like now?
2 different frequencies together.
oh,
That
it's a
doesn't-
subsequence.
I'm not sure. Subsequence. I want to share. I'm not sure what it is. Yeah, but sub-frequency. Okay, so what we see now seems very erratic. Just for 2 whistle, it was such a clear sign before it, but now, or cosine, right? But now it looks like this. So if you think of every note as a vector, so suppose one of the note was actually a sine function, and the other note was, let's just say, cosine, but of 2x, because it was different frequency, right? What is the sum of these 2 vectors, the new vectors? So does any of them has a direction? No, we don't have the geometry anymore. Can you tell me about the angle between these 2 vectors? What does it even mean, right? But you will see, I'm not sure if you will see it, to be honest. In math, you have actually a course that deals with it, but it is very useful You'll see in a second. So this looks like teeth, to be honest. But in any case, you see any two, and it's always, I'm always surprised is what we get here. When I take any 2 frequencies and sum them up, I always choose something random. It always looks very different. So this is basically what you see.
It's an approximation of sine postgraphs, right? That last function.
This is the addition.
No,
This is what your ear is getting, because
oh, I see.
your ear getting the air pressure from me, and their ears, the computer ear, the microphone gets the air pressure from me and from you. It sums up to pressure is the sum of the pressure.
But the part in mathematics you're talking about, isn't it? There's like a area in mathematics that says that you can.
The area of
any
mathematics
graph.
is called Fourier analysis.
Yeah.
You definitely use fast Fourier transform in algorithm. in algorithm course, but usually you have no idea what it actually means. You use it, but you don't know. So the word FFT, you will know what I'm about to do on the software is FFT, but I'm explaining the, let's just say, more physics part of it, but it's still mathematics. Okay, so we have the two vectors. One of the things that we will learn within that course is when you have a vector which is the sum of a few directions, usually the directions are the axes. Sometimes it will be something else, but you have some axes, which will be called a base of vectors. And I'm taking a vector which is a sum, it's built from certain from the axis. Sometimes we wish to go back, I mean, to separate this vector into its two parts, Sammy whistle, Sammy's note, and mine. Can we do it? Do you suppose that from here I can figure out it's the other way around, meaning look at this, you need to figure out from which nodes is this function built? And is there only one way to do it, right? Specifically, because the way we built it, we know this is sine of x plus cosine 2 of x. But maybe also it's cosine of 4x minus sine of 3x, right? You see what I'm saying? Could one force be separated into different רכיבים, parts? Okay. Oh,
Yeah, I don't know if factors will be more fitting in this case.
in
What's
physics,
the word?
in physics, when you have I don't know, like something that rolls down the hill, and you have the gravity, then you split it into two forces. Components. I think, yeah, I think components is the word I was looking for. So we'll answer this question exactly algebraically, whether there could be different decomposition into components or only one way to do it. Okay, but now and how to do it. But now I will decompose it into components, and actually the software will do it for me. I go to the spectrum view. Okay, and I'll explain a bit about it. And also look here. I can decide, really, it's really FFT. I don't know if did you hear about FFT yet or no? In algorithms, you will. But in any case, it's really, I can really decide if you identify, recognize these numbers are power of 2. I can decide FFT is always done in powers of 2, and I can decide what will be the size of each frame. When you learn about it, you know this is actually a mathematical parameter. The software has allowed me to use it. I changed it just for you to see. It doesn't really matter now. And we see the two whistles, and I explain to you what you're seeing. What do you hear now? You hear two notes. Agreed? So this axis, what does this dimension, what does this axis tells us?
Time.
The time, exactly. This is the time. Can you guess this axis?
Maybe frequency.
That's the frequency, exactly. That's a higher note, that's a lower note. By the way, I can actually tell him to give me the actual notes. All the jumps means that we whistled horribly, but I'm not sure if you can see it, but that's D diez or E bemol, mi bemol, and this is me. So this is your, no, mi, do re mi fa sol, E.
Right.
Not me. Yes. So this is you whistled most of the time at E.
Yeah, no, I
E6.
went down in chromatic steps.
Yes, yes, yeah, on purpose.
Yeah.
And I was A in lower octave. In any case, in any case, this is what autotune, by the way, does. It fixes the sine and cosine, so it will be the actual note. But and what is the third axis here? So we said this is time, this is frequency,
Volume, intensity,
amplitude, and where is it? How can you see it?
brighter.
It's the color. It's the color. You use color to make it a 3D graph, basically, because the color yellow here says that this frequency at that time was high, while the purple, rather black colors means the amplitude was really low, meaning this frequency did not really occur there. Okay, but now for the so first of all, in order to show us this graph, some serious linear algebra is happening. Okay, because it takes it and factors it. Yes.
It also has an echo very top.
Yeah, it's not exactly an echo, it's an overtone. It's an overtone. And yeah, and this is my overtone. It's twice.
Yeah, you
My
can see
frequency
across
was
the-
900, so the overtone will be at 1.8 thousand. And your, because you were about 1.1, it will be at 2000 something. Yeah, so that's your overtone. Okay. In any case,
It's below as well.
no, it's never below the
It's
overtone.
above.
Yes.
Wait, frequency is the amount of waves in one. Okay, right.
Yeah, and then yeah. In any case, what can we do after we separated the components? We can delete the annoying sound of Sammy.
Oh.
Sorry.
So
So actually, sorry, not sorry. And
you'll still have my overtone now.
yeah. That is super interesting. We have in this class constant sound.
The
9. It's
conditioner.
probably one, but 9, it's really high. I don't usually see things that
Oh, so you
high.
can't
Where's
hear
the
it.
dolphin?
I do it a lot, and I never saw a line this high. Are you seeing it even? I'm
Yeah.
not sure.
Maybe it's just your computer.
Yeah. No. I
No,
do
it's
it all
like
the time.
sound
No.
coming-
There is a sound here in this room. It wouldn't
There
be.
is a sound here.
Ah,
Those
it could be.
have
Wait. But it could
Would
be
be-
an echo. No, this is your echo. It could be. I see here
A
it's
standing
3000 something. Maybe it's an echo of something smaller.
a standing wave of something.
Whatever.
Would we be able to hear it? Like, is it?
Yeah, it's within our sun wave.
Everyone,
So it's that.
everyone goes
It
quiet.
could. By the way, it could be the computer. You're right. You know what? Maybe it's the fan of the. Yeah, maybe it's the fan. Maybe it's the fan. Yeah. Okay. So it's not that surprising. In any case, let's delete that too. And what will we hear now when I play it? The reason you're hearing it twice is because of the zoom. Because we hear it from my computer and then on the. But you just hear me. Let's. See, just without Sammy. So this is linear algebra. It's best. We look at everything as vectors. We can remove components. We find the scalar that multiplies by each vector. We nullify it, make it 0. So we make the vector disappear. So, and that is very useful. This is a very good use for linear algebra. We won't speak about it too much, but specifically. But the beauty of it is that it is just certain example for linear algebra. So we started with geometry, we figure out some algebra, and then we use it on sound waves. Okay? And by the way, it's even more than that, but we will not get into it too much. But sine and cosine are perpendicular to each other algebraically, and that also help us behind the scenes when calculating that. That's some linear too. Okay, let's just, for the sake of writing something down, I will copy these pictures so you have a good memory of me deleting Sammy. But let's bring him back.
The way you put that made me feel very uncomfortable.
Okay.
Sounds like
The way you asked me question lying on your back before made me feel uncomfortable.
Sorry.
So now we're even. In Israel, you don't really care if someone feels uncomfortable. It's even good. Okay. I made it.
Certain dominant.
Yeah.
What's it?
Asserting dominance. Yeah, that's you're joking, but yeah, that's the way. Like להידחף בתור, pushing in line is a way to assert dominance. It's true. The alpha male always moves to the head of the line. Okay. So and this is enough introduction. Now let's do the accurate definition. Now for the definitions. So, definition. And a set V along with a field F and two operation sum addition and scalar multiplication is called a vector space over F. So we say that V is a vector space over F if the following properties hold. So it's the same way we looked at fields of numbers, right? We say, what are numbers? So you can have many philosophical, geometrical definitions, but we took the algebraic route, which meaning we take a set of any elements, we define operations, and then if the properties hold, it's called a field. So here the same way, a vector space, it's not a magnitude and a direction, that's the geometrical interpretation. It's just a set of elements with operations. And with this definition, now I can say it again, the sound wave, the notes, is a vector space because I can sum the note, I can multiply them by scalar, which is the amplitude. All of the properties will hold, and I have some vector space, and all of the rules and theorems that we will learn about vector spaces hold for this vector space as well. You see what I'm saying? And remind me after definition, I will quickly show you something that connects the two, both the complex numbers and the sound waves, and it shows, I don't remember if I promised you to show you, but I told you that the complex numbers are also measure amount, and the amount that complex number measure is the amount of a note. Okay, and you can actually predict how notes will sum up together using complex numbers, but we'll do it afterward. First of all, I wish to write the properties. So property number one is the closure, closure for every V and W in the vector space and scalar in the field, it is true that V plus W is also a vector, and A times a vector is also a vector. That raises an interesting question with the nodes. If nodes are vectors, what is the sum of two nodes? So it's not a node or anymore, right? Yeah, it's a harmony.
It's 3 notes again.
Yeah, whatever. Yeah, but,
Also,
yeah. But every sound is a vector there, not just the notes. The notes are like more like the basis. It's not really the basis, but it's the axis in a way, but they're not because they are like. Why am I saying they're not? Because if a note is off key, it's still a sound, whether we like it or not. We can't say it's not. And the problem is, and the reason that we don't
It's
work
not
with this
scalar,
vector
not
space too much, that's its dimension is infinite. And in this course, we'll only work with finite dimensions. Okay, so that's the reason we don't actually do a lot of examples with the sound vector space. But every sound is a vector. The notes are like axis in a way, and there's some are points in the vector space. Yeah, I like to say it's harmony in a way.
I was going to say
Cold בעברית we say.
you can come back to it when we talk about the linearly independent vectors because every node is an independent vector.
Yeah. And it's more than that. Every node is two independent vectors. Dimension of just one node is two. It's surprising. Maybe I'll show you why, but that's the reason we have both sine and cosine. What's the difference between sine and cosine?
90 degrees.
It's the same function, just moved, right? So why do you need both of them? Exactly linear algebra, because we're given sine and cosine, you can create any nodes within the same frequency. But we won't do all of that. Yeah. Okay. So I'll do some of it because I find it very interesting. Okay, closure, commutativity, and for every V and W in the vector space, every two vectors, and I don't want to write it is true that just write a comma and not even V plus W equals W plus V. So that property is just for the addition, not from the scalar multiplication, because with scalar multiplication, you always write the scalar on the left, and that's it. You never write it on the right. It has no meaning whatsoever, so we cannot speak about commutativity. Associativity. I write the rule and then I see what do I need here. So V plus W plus U equals V plus W plus U. And in scalar multiplication, A times BV equals A times B V. I think these are the one we need. So I'll write in short that V, W, and U are vectors, and A and B are from the field. And V, W, and U are from the vector space, are vectors, and A and B are scalars from the field. Scalars are simply numbers from the field. Okay, so we need that as well. Next, 4. Zero vector neutral. I just call it zero vector. And there exists a zero of the vector space with sound. what would be the zero?
Quiet.
No sound.
Silence, exactly, silence. Okay? In the normal vector spaces, I don't talk about them a lot now because we'll talk about them a lot in the future, but that's the origin. The axis, the origin of the axis is the zero vector, basically. That's the zero of the vector space. So there exists some zero vector such that for all vectors in the space, it is true that v plus 0 is v. Double. Sorry. Okay, that's v. So you must have a zero vector. Next, it's inverse, why not? Opposite I will use. Because in Hebrew we say inverse for multiplication usually and nigdi where it's addition. Opposite vector for every vector in the vector space there exists a negative, so-called the opposite vector in the vector space, such that what is their sum?
Zero V.
Yeah, it's the zero vector, exactly. It's really like a field, but a bit different, a bit different.
Is this how they do noise cancelling?
With noise, it's not possible.
It's not exactly the same.
Okay, now I must
We can
answer
do
you.
Do and
Just did before we came here. It's incredible. It's incredible. I was just working on it. You'll see. Alright.
You can have some that was the
First of all, I will. I wonder if it will work, but I can you see what I'm showing here? Okay, now it's not there. Wait, I will show you. I need to figure out where exactly in the movie I do it. She sent me another one. Maybe that's not a good one. Just a second. No, that's the one.
That's a reverse, yeah.
Okay. Look.
No, we'll keep it.
Okay.
I didn't realize it.
I'll show you what's going on in this video. We're recording a note. Okay, here is the balance of the right and left speakers. They are both at 100%. What I'm doing is I'm muting one of the speakers. What do you suppose will happen to the loudness of the voice?
Depends on the configuration, but in
Where-
theory it should have.
What?
In theory, it should have.
You say if we're muting, it should lower the voice, right? One might think so. But in fact, it enlarged the sound. Muting one of the speakers made the sound louder. Why?
Because
Because the configuration of the speakers was noise canceling. They were canceling each other. And when I muted one of them, it stopped canceling the other. And how can sounds cancel each other out?
destructive
being exactly
interference.
the opposite.
By taking the minus vector, and he was completely right. But in waves, you can look at it quite easily. when you have sine,
It's like just having like a.
what will cancel sine? Minus sine, exactly. And what happens is that one is the maximum air pressure, the other one is at the lowest, and their sum stops the wave from happening. It's pretty much canceling out. So that's the theory. Noise cancellation headphones work that way. But just today before this class,
Chance.
by chance, I just did this experiment on my computer. I don't have the speakers here, but that's the video you just saw.
Yeah.
That's noise canceling in the real world.
You didn't say it, it's like explain the aspect, destructive interference.
Yeah, but this is
Real world
it's
destructive
real.
interference.
It's real. Okay. So okay. Yes, it's real. So yeah, and it's all linear algebra. It's so amazing. Yes, I like it. So opposite vectors. So what would be at Sammy? Do you have a few more minutes or because
Yeah.
yeah, I just will need to finish our two properties more, 6 and 7, then we'll take the break. So 6, when we did fields, we had the neutral element for addition and a neutral element for multiplication, right? But here the multiplication is by a scalar. We don't choose the scalars, the field is there. So the unit scalar property basically says that for every vector v, it is true that if you take the one of the field, the unit element of the field, and multiply it by the vector. So the unit element exists because it's a field. I don't need to demand that it exists. But what I will demand is that when you multiply by the scalar 1, it won't change the vector. Okay? And lastly, what was the last operation property, sorry, in fields?
Distribution.
Distribution. So here again, the distribution will be a bit different. That is distribution, and we don't have inverse for scalar multiplication. I just say it by heart because you cannot cancel it. Once you multiply the vector by a scalar, you have a vector. You can never get back a scalar anyway. So there is no inverse here, but you do have distribution, which says both a times v plus w is av plus aw, and also a plus v, a plus v wv is AV plus VV. So you have two different distributions that can happen. We demand them both. So these 7 properties are what defines a vector space. Like I said, there are many vector spaces in general. We will focus mainly on the normal, let's just say, vector spaces, and after the break I will show them to you. So now let's take a break until 2:20. You got it.
What theory are you going to do?
Let's do the thing like next week. It's like noise cancellation. Okay,
it's-
noise,
I don't know, it's
like
like
a
a-
sound with the minus attitude. How it can be like.
What is minus? Minus
After that, the next study, I don't know.
Yeah, I agree. That's why I learned math, by the way. I had that choice between the two.
They just simply can do a normal system to submit the homeworks because we don't know how we have it, but we can do it. It's like,
Yeah.
okay,
Today with ChatGPT everything.
yeah.
Okay. So I wrote to myself to give you a note about sound waves and complex numbers. I will do it really quickly because again it's extra material, it's not the heart of the course. But take the waves, consider. So consider the waves cosine and sine, each of amplitude 1. What would be the amplitude of their sum? So before I've shown you that if the waves are located I don't know correctly, but a certain way, they could cancel each other out and even make the amplitude lower. So now I'm giving you two specific waves, cosine and sine. Say, Sammy whistle at a certain note in cosine, and I whistle in the same note, same frequency, but sine. So what would be the amplitude of both our sounds together?
Still not.
So that's the question. It's not obvious. Could it be? You're saying it's the same amplitude, but the question is whether it's louder, softer, same, and what number exactly. And the nice thing is the answer comes from linear complex numbers, sorry, because the wave has two properties. It has its amplitude and phase. Where is it located? So think of cosine as like the base wave. So what is sine? Sine is a cosine that was moved by half of pi, right? So now think of it as on complex numbers. This is one with zero movement, angle 0. One with angle 0 is 1.
Yeah.
This is one with angle 2, half of pi. What is one with angle half of pi?
It's like, fine.
What complex number? I, exactly. I'll write it. Sine is, writing math. Sine is cosine moved by half of pi. So in complex numbers, you can think of a cosine as the number 1 and 0 phase, which is angle, and sine as magnitude 1 and angle half of pi, which is the complex number I. So Sammy, I'll bring you up to date.
Thanks.
We're looking at cosine and sine, two specific sound waves, each of them of magnitude amplitude 1. And my question is, and I'll let you answer specifically, if I sum them up, what would be the amplitude? If each one of them is, say, 1, what will be the amplitude of someone who hears both sine and cosine? First of all, will be this, yeah. Like really voices, right? You
Yeah,
whistle.
It'd be the same.
Can I
But
update
two
my
of
answer?
us, two of us are whistling. You would expect usually to be higher, louder, right? But we saw that sometimes it cancel each other out, right? So that's the question.
It depends.
So that's the question. Yeah, no, but it doesn't depend because it's cosine and sine specifically. So it's really a specific question. And then I said, it has to do with complex numbers. Think of cosine as the base one, meaning one and angle 0. And then sine is 1, but it's moved by half of pi. So it's angle half of pi. The complex number is I. So I'm saying cosine is 1 and sine is I. Okay? So one could tell me, but that is complete. Yes. So someone will tell me, okay, so you decided to call it I. You decided that the movement is actually an angle. Anyone can invent whatever they wish, right? The nice thing that it actually works. So in this sense, the amount of the wave of the sum wave will be 1 plus I. Then you say, this is weird. How could that be an amount of a wave? But what is 1 plus I? It's the square root of 2 with angle pi over 4, right? So let's sum up sine and cosine and ready to be amazed. F plus G. That's the sum. First of all, what is the height here? Square root of 2, exactly. And where did it move? Where is the height located? Pi over 4. So actually the complex numbers measure the amount of waves, and their addition measure the amount of waves, and their multiplication. That's simply the language of waves. And as is well known by physicists, waves are the basis for everything, basically. Not everything, but most things. So complex number, actually, some people say they are imaginary. They are not imaginary at all. They are quite real, and obviously very useful, but they are quite real in that sense. So that was Shara. That was extracurricular, but I think it's nice, and I'm done with it. Sorry. Yes, Samuel. Yes.
Just for a second.
Yes.
Okay, thanks.
Okay. I'll just tell you one more minute that the reason I'm so excited over it is because the way my life experience, I did a bachelor degree during high school, and then I went to the army. I went to an intelligence unit. I went to an intelligence unit, and we learn a bit about waves because of networks, because of communication, right? The way, I don't know, a smartphone transmits its data. And then I saw the actual uses to a lot of the math I was taught in the degree. Now I was so amazed by both things because it was hard for people to understand without the math, the actual things they need to know about waves. And without the actual uses, it was hard to understand the math, and only the connection really lets you understand science. For me, that's really science. The whole story here that we started with geometry, and then we said, oh, algebra will help me. Where was it? Oh, algebra will help me do geometry much more efficiently. And then, oh, if we see this algebraic structure somewhere else, it could help me use geometric tools basically on things that are not geometric at all, and that's science. Part of science, but still. Okay, so moving on, the main example for vector spaces that we will use is F n. I defined Fn, right? It's the
Vector of size n.
sequences of size n, right? F2 is couple pairs, F3 is triplets, no? Okay.
I'm not sure. I thought it was vectors of size, whatever.
And what?
Vectors of size, like whatever.
Vector, vector. Yeah, but what is vector? It is, it's circular. So Fn, yeah, it is. But vector is a sequence, right? It's a sequence of number. It's all of the that's I'm just saying that mathematically without saying vectors, that's a sequence of n numbers, right? So Fn are all the sequences of size n, such that all of the numbers are obviously from the field. Okay, and this is not enough over, first of all, over the field F. So what does it mean over the field? We're saying where did the scalars come from, right? So we take the set of, if it's F2, it will be the set of pairs. If it's F3, it's the set of triplets and so forth. And we wish to say that it's a vector space. In order to say it's a vector space, we need to define operations, but the operations are the one you know. What do I mean? If I add x1 to xn and I sum it up with y1 to yn, what is the addition? Right.
It's
X1 plus y1, and so forth, xn plus yn. So again, it shouldn't be new to you. I've shown you this example before here, right? I asked you to sum these two, which are in R squared, R2, because it's pairs of real numbers. And you did the addition intuitively, right? Now I'm just writing it up accurately, so it will be clear and accurate, but it's nothing new. It's nothing new. And also, what is C, scalar C, times the vector x1 to xn? Yeah, again, quite intuitive. This is a vector space. We won't prove that this is indeed a vector space, meaning that all 7 properties hold, but it is. And it's very easy to do. That's the reason not to do something is sometimes because it's hard, but otherwise because it's too easy. So this I'm not doing because it's a complete waste of time. You just plug in the operations in the formulas above and you see everything works, okay? So this is the most basic vector space there is. We may see more, but this will be always the go-to. And I wish to say that specifically R2 is called the plane Hamishor, and not from Qatar, but R3 is it doesn't have a good name. What would you call it? I'll show you.
I mean, a three-dimensional plane.
That's R2. Not plane.
I mean,
This is R2.
Space.
That's the plane. And if I go here, you would say the 3D space, right? Yeah. In Hebrew, that's a cultural thing. In Hebrew, we call the R2 Mishor, and R3 in high school is usually called simply space, merchav. Hamerchav. And for us, it's really annoying because for us, everything is space. It's just different dimension, right? But that's not the main problem. And R3 is called the 3D space. We can imagine these two, only these two, okay? But the algebra works the same at all vector spaces. So what I'm saying is that when I give you examples and I wish them to be visual examples, I will usually use R2 and R3. Anything else usually is unimaginable. And for example, let's look at the vector space. Let's look at the vector space, which is C cubed over C. Meaning the scalars are complex. You could look at the same vector space over R as well, I won't. But what does that mean? So could you give me an example to some vector within that space? So it's basically just a triplet of complex numbers. So for instance, 1 plus I is a vector on this space. This is also an example where geometry has left the building, right? I have no idea what geometric meaning does this have, but algebraically, it's simply the same. I do everything I did with the real numbers. I simply do it with the complex numbers. I can sum two of such vectors together. I can multiply by a scalar and get something. And when we'll have theorem, they will hold for these kind of vectors as well. So this I have no visual meaning for. R4, you can say it's R3 plus one dimension. You can also not imagine that, but it's less abrasive than when the scalars are the complex number. That's much harder to imagine. I try to give you some sense of it with the waves, but I don't know how sounds in 3 dimension will work. Yes.
Is there a special categorization for these kinds of vector spaces where the fields could also be represented as a vector?
Not really, but I every field is a vector of dimension 1. So you say complex numbers are vectors of dimension 2. So there is a study, Galois theory, that maybe there lies some answer. I didn't study Galois theory myself, to be honest, but I won't say a lot about it, but I think it was Hilbert. Let me make sure I'm not quaternion with something a bit similar, I think, to what you're asking. Hamilton, not Hilbert. So he says, okay, we know the complex number field is a plane of real numbers. So the thing is looking at one field as a vector space of another field. And he says, could there be a field which is a 3-dimensional space of real numbers or 4-dimensional space? So basically, long story short, there is no such a field, but there is a very good algebraic structure of 4 dimensions, the quaternions. Let's look at it in English. I'm not sure why am I in Hebrew. I indeed know how to write quaternion. It's not that. And there is I'm not sure if it's history or urban legend, but they say that when he finally figured out how to do it in 4 dimensions, he was so excited that he marked it on a bridge here as he walked on the 16th of October, 1843. So William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for the quaternion multiplication and cut it on stone on this bridge. Where is the where is the marking on the bridge? That's your story. I don't. I'm kidding, of course, but yeah. So he asked himself something similar to what you asked. So you're thinking of great mind.
In
Thinking of,
quaternions, yeah.
yeah. No, just you think about the great questions of life. Solving it something else, but you're thinking about it.
You're in the right direction.
Yeah,
Not there
exactly.
yet.
That's the first step is admitting the problem, right? Yeah, solving it. That's the last step. That's the pessimistic end of that theorem. First step is acknowledging the problem. The last one is solving it. Okay, so but we won't do it in this course. Okay, it's more like I said, Galois theory, I think. So I give you the hard example. We usually work with the easy examples, but sometimes I ask about the harder ones. And also, in order to understand why do we define everything so abstract, that was a lot of my point this lesson, is that because you can say, a lot of students say, why do you define it so abstractly instead of just using R2 and R3, which are useful? Because you see that sometimes the abstract notion is very useful in places you will be surprised to meet it. And it happened a lot during history, sorry. For instance, even encryption. Have you heard about RSA encryption? It's basically the utilization of the most benign mathematical questions as to if you take a natural number and you take the power of a prime number and take modulo of the prime number, what will you get? And Fermat and Euler deal with these questions and they solved them just because they were interested in them. And few hundred years, a couple of hundred years later, I think, I'm not sure when Fermat and Euler were, lived, they use it for encryption. They figure out this mathematical theory allows us to do encryption.
Three Israeli guys.
And no, not three Israeli guys, one Israeli guy. The S in RSA is Shamir. The rest are not Israeli.
I think they are for that, sure.
No, not Israel. Definitely not Israeli. Maybe Jewish, but not Israeli. You can make sure. Okay. Adi Shamir from Technion, but also Rabin from Miller Rabin was from the Hebrew University. I never forget if he's deceased or not. Shamir is living. Rabin, I'm not sure. Not the Rabin, but I'm sure it's not. Okay, so we have vector spaces. Like I said, the main one is the main type is some field to some powers, and we work with. And what is the next question we ask ourselves? So, given R cubed, for instance, what kind of question can we ask about that vector space? I wasn't that terrified this time. Okay, we should measure that with the Adobe Audition and see how it looks. Okay, what can you tell me about the vector space R3?
That's three numbers.
Yeah.
3 what, but not numbers.
Real.
3 what? No, but that's the definition. It's triplets, right? But something more, I don't know, vectory, let's say. Okay. How do you say we call this space?
Space.
So what does it has?
3 dimensions.
Yes, it's three-dimensional. It's three-dimensional. Dimensional. we will define dimension and prove that claim. So it's not obvious why is it three-dimensional. Mainly because we didn't even say what a dimension is. So how can I count that which I don't understand? But we will, right? We will define. But I'm saying that's probably the only thing, or the main thing I can say about this space. It's three-dimensional. That's it. So the main study will be of vector subspaces, which are basically, I'll define it in a few rigorously, which are basically vector spaces contained within larger spaces. Then we have some interesting questions. For example, I'll start with an example. If you're trying to understand what the heck am I doing, so now it's another introduction to subspaces. Okay, vector spaces we defined. I don't have a lot to say about vector spaces as vector spaces, but I will define subspaces, and then we'll have many interesting questions about the subspaces themselves and how they interact and whatnot. So I'll give you an example. Look at U, which is all of the vectors of the type T times 1, 2, 3 plus S times 4, 5, 6 plus R times 7, 8, 9, such that S, T, S, R are all real numbers. And I just want to make sure that you understand that this is a subset of R cubed. Do you agree? I took triplets, they are all within R cubed, the three-dimensional space. I multiplied them by scalars and I summed them up. Due to the closure property, they all remain within R cubed. So U is a subset of R cubed. I'm not sure what the subspace is yet. It is a subspace, but I'm not sure what it is and why it is. But this is clearly, strict mathematics wise, a subset of all the triplets. And now I wish to ask you questions like, what is the dimension of U?
Yes, in three.
You would say it's 3. So if you say the answer is 3, if the dimension of U is 3, then is U actually equal to R cubed, or could it be smaller?
Um,
Necessarily.
sorry.
Always wrong about it.
Oh,
Ah,
no, no,
2S, 2, not, okay, sorry, yes.
it's the same size.
I'm just wondering.
But
Your
wait, sorry, Thomas, I'm just wondering to make sure you're not supposed to be able to answer it because you don't know what the dimension, you don't know what their properties, but I'm trying to show you what kind of questions are there to be asked. And we will learn how to, what they mean and how do we solve them. And the nice thing about linear algebra, all these questions will be solved by taking matrices
and Gaussian
and Gaussian elimination. Everything comes down to that finally, right? But now we're adding meaning to the whole Gaussian thing. So yes, Thomas, and then you ask.
What you're doing here is grabbing three different vectors, multiplying by an arbitrary number, and then that's all of the combinations that are in U.
Yes.
Okay.
Yes. These are the operations we have in the vector field, multiplying by scalar and add, addition, right? So I do the operations that I have with three given vectors. I start with this example because this one I can show you geometrically.
That it's not free space.
In general, I can show you geometrically what is happening here. Every vector is some kind of arrow. When I multiply it by a scalar, the arrow either enlarge or being smaller or go to the other direction. And when I sum them up, I'm moving in space in these three directions. So the question is, if I take all the places that I can get to, what can I say about this set? Is it a space? What is its dimension? If it's three-dimensional, does it has to be the whole space, or could there be a smaller set, but still of the same dimension? Everything here are very good question. It will take us a few lectures to go over everything. Maybe a lot. It's like a main thing about the course. It's like I told you, it's chapter 4 out of 5. After vector spaces, we will move on to linear transformation. But these are really the kind of question we wish to learn about in vector spaces. And another question, sorry, just one last thing. And given a space, let's call it W. Why is it not in the center of the page? Something does that. I'm not sure why. Okay. Given W, which is all the x, y, z's such that x plus y minus 2z equals 0 is a W a subspace? What is its dimension? Is W is the intersection of W nu a space? What is its dimension? How about the union? And so this will be the kind of question that we're gonna answer. Yes.
I have maybe dumb question, but how is t as a vector?
T is not a vector.
Oh,
T is a scalar.
Okay, yeah.
Yeah, I multiply the vectors by scalars and then I sum them up. I will do it in a minute in GeoGebra for you to understand the question. As again, the nice thing is it will take us some time to understand what these questions even mean, but actually solving them will be quite easy. It will be, like I said, you'll use matrices. You just need to know what matrix and what can you deduce from its echelon form. That's the main thing about linear algebra. Okay. So let's study these examples geometrically using GeoGebra.
So the tool just throw the phone up where they got.
Yes. Okay. So let's start with the first example. I'll take the first vector 1, 2, 3, and I take the second vector 4, 5, 6. So I have two vectors. Does U come before V in the alphabet?
Yeah.
That's the reason. He always used U before V, which is so confusing to me because I would use V for vector first and then U. Okay, so we have two vectors, right? If I sum them up like they are, I will get diagonal of the parallelogram, this, right? But if I add scalars, A, B, and I multiply each of them by the scalar. So if I multiply just AV, well, A is 1 now, so it's not interesting. But if I multiply AV, it makes it longer or shorter. Agreed? And if I take a negative scalar, it goes the other way. Agreed? So let's keep that. Let's give it a color as well. Bright red. And AU is the same here. Let's green. Bottle green.
Will be you.
Right. Sorry, BU I should have done. Thank you. So again, this does that with the other vector. And I want the purple one not to be V plus U, but to be AV plus BU. And now, when I change the scalars, I also change the addition. So my question is, first, where does the set of all the heads of the purple vectors, I take just the head, all these dots, and I take the set, what will it look like? Yes. So what do you think it would look like? And let me describe to you. Suppose you're in New York, and you can, with your car, you have two directions. Turn to the right and go straight ahead. But you also have the scalars, right? So you can multiply by the negative scalars. So instead of going to the right, you can go to the left. Instead of moving forward, you can go backward, right? So these are your abilities, and to which length that you want. Which area of New York will you cover? All of it, right? So why did I say New York? Because if we're thinking, New York is rather a new city, and it's built, unlike Israel, in straight lines. So a lot of mathematics is hard. It's easy, to describe because it's like a table. It's like a matrix, basically. It's a matrix. In any case, you will cover all of New York. Do you agree? So now take the same example and skewer a bit the vectors. Not skewer, skew, not skewer. Skew the vectors a bit. So what will be the form that will be created from these two?
The same shape, but up and not.
What do you call that shape?
Plane.
Plane. It's a plane, right? On the floor, it's the plane of the floor, but if you skew it a bit, it's some other plane. What would you say the dimension of it will be? 2. The plane is two-dimensional. So when it's on the floor, it's a bit easier to grasp because it says the floor is X and Y only. When you skew it, it's within the three-dimensional space, but it's still the same plane. It's still the same object. It's still two-dimensional. And the easiest thing about dimension, I think, to know is directions. I'm asking how many directions there are. And in a plane, you have two directions. It's not completely accurate because you have infinite directions, but you take the minimal amount of directions you need to be able to travel everywhere. And that will be that literally will be the definition, not literally, but that's really close to it will be the definition of a dimension. It will be the minimal amount of vectors that you can create all the space from them. So in a plane, it's two. Given two vectors, you can create a space. If you have only one vector and you multiply it by a scalar, what would you create geometrically?
Another vector.
A what?
You said one vector.
One vector.
Yeah.
Only one vector. You're multiplying it by which scalar you want. What kind of geometrical object will you get?
Another vector.
But all of them, all of
Yeah.
the multiplication, what does it draw? The set of all the vectors. If you take, look here, take V,
The plane.
no, just one vector. Oh,
Ah.
I took U instead of V, sorry. Okay. You take V, and then you do only this, only multiplying by scalar. What do you get here? A line. A line. If you have one direction, you can create only a line. What is the dimension of a line? One dimensional, because one direction creates a line, not a plane. Two directions create a plane. Okay, that's the idea I wish to impart to you. Okay, yes, Sam.
Isn't a line? Oh, what you're saying, the space of the line.
The set of all the points in the line, yeah.
Right.
It would be a space.
Okay,
It's infinite.
that's a bit more confusing because
Why?
because you can't represent lines on a 1D space, only on a 2D space.
You can
Okay,
in
on
a
1D space
silly
it'll be
way.
dot.
No. In the 1D space itself is a line. A space, so the subspace will be the whole space itself. So I agree, it's silly, but
Okay,
it's
so
true.
yeah, fine.
And in the plane, a line would be a subspace, and in the and in any higher dimensional space, there are lines within them. In 2 and 3, we can imagine them. It wasn't by mistake that I didn't mention R1 as a vector space as the one it's easy to imagine because it's confusing. But it is a space. Even one dot is a space. Only the zero vector, the origin, is a space. It's 0-dimensional. But these are, again, the easiest to imagine are plane and 3D. These are the things we can imagine quite easily.
You have a negative vector space.
What do you mean negative? It contains the negative.
No, I mean like r to the -5.
The size. No, but you can say half as well. And not that I know. There are some theories. I know that there are. I don't think there are anything negative, but I think there is theory about dimension half. The dimension of the space is half, but not in this course. In this course, natural numbers only. Okay. I'm not sure what would be because the definition was the sequence with our number. There is no sequence with -1 number with that numbers. There is no sequence with -1 numbers. So negative dimension, I don't think there is, but rational dimension there is, but it's not what you think it is.
Great way of keeping it negative.
You wouldn't like it. Okay.
That's assuming we like it.
Yeah, no, that's not. That you have to study, that you so it doesn't matter if you like it or not, that you don't have to study and you don't like it, so I don't see any reason. Okay. You like it, Thomas, you don't fool anyone.
I like math. Math doesn't like me back.
Yeah. You're like a stalker of math. You're watching it videos and say, oh, it's so beautiful, but then it ignores you.
And puts me bad grades.
Yes, exactly. Rates you 5 out of 10. Yes. Okay. So where was I? I remember. So I put only, I don't know if you know this, but I put only 2 of the vectors in the example. I put 1, 2, 3, and 4, 5, 6. But the original question was about 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you know why 6 is afraid of 7? Okay.
7, 8, 9.
Yeah. Okay, sorry. And my question is,
That doesn't work the same in Hebrew, does it?
no,
You get to use the jokes you usually don't get in Hebrew.
yes.
Great, that's
And there is another one with y69 in front of 70 because something and 71. But I'm not sure the rest of the joke. Okay, sorry. 7-1. Okay. In any case, what will happen just a second before I'll draw it? What will happen when I add the third vector? We saw that these two vectors created a plane. We didn't see it, but we visualized it. Let me write the actual plane. The plane is x minus 2y plus z equals 0. And when I rotate it, a second, and you will see that indeed this is the plane of these two vectors. So this plane, I'll explain this plane. I want to write something of what I said by heart. This is the plane created from the vector 1 to 3 and 4, 5, 6. It is a two-dimensional space within R3, which is the three-dimensional space. So subspaces would have smaller dimension than the original space. That's kind of what we want. Okay, a line is one-dimensional, a plane is two-dimensional. Okay, and the next question is what happened? What will happen when I add the next vector? Yes.
nothing. Because we can achieve that vector from summing
Yes.
previous vectors.
If I add the third vector is 7, 8, 9, we can see that the third vector in this specific case is apparently on the same plane as the other two. It did not add a new direction. If you think about the cab drivers in New York that could go left or right, straight or backward, assume you demolish the buildings and you allow them, I'm not
Anarchist suggesting anything.
anarchist or I don't know, Saudi, sorry, okay. Assume that we demolish the buildings and we are allowed to move in diagonal. Does that change the places that we can get to? No, because the diagonal is already within the space that I covered. Okay, this is the idea of linear dependence that we will learn. Okay, the third vector is linearly dependent in the first two. Okay, in this introduction, I'm pretty much trying to show you the entire chapter. Okay, so I'll write. I will write the idea with the cab drivers of New York, and I
Yes. It was Gaussian elimination in the end.
yeah, it will be Gauss elimination. That's true. So we see that the third vector is redundant in a sense. Redundant in a sense. Think of cab drivers in New York.
Comes with B, but
Okay. If they can move forward or to the right, and I will give you specific vectors for that. That's 1, 0, 0, that's to the right. Yeah, because X is there. And 0, 1, 0, that's forward, right? Okay. And any scalar multiplication of these vectors, which allows left and backwards, because we multiply by -1, they can cover all the city. That's all the A, B is 0. Okay, I did a terrorist joke before, but I'm still keeping on the ground. I'm not using planes. Okay, so we keep it on.
you're using planes, not spaces.
Yeah, yes. I'm working at doing some exercise software using ChatGPT, and I told him to ask in Hebrew the intersection of planes. So he said, "What? What is the chituch of the two metosim?" Yes, yes. Okay, but it was a few months back. I hope now we won't do this translation error. In any case, you get everywhere. And if you allow the drivers to demolish buildings and move at direction 1, 1, 0, they will not cover any new ground other than the locations of the buildings, obviously. Okay. So in that sense, 110 is redundant, and it doesn't have to be simply the XY space, right? It could be the whole thing skewed in R3, and the really mind-blowing thing that we can't imagine is doing everything in 4 dimensions, 5 dimensions. So what is a plane within the 4-dimensional space? I have no idea what it looks like. Algebraically, I can answer the question of linear dependence, whether one of the vectors is redundant, just as easy by Gauss elimination. We will see that the way to answer the question is Gauss elimination. As such, I will put the vectors as the column of a matrix,
Why not the rows?
because that's the way we will study. We'll see why. We're not just putting it in a matrix because that's what we do in linear algebra. There is a theory behind it that gets you to this matrix. You will see it. You'll see it sometimes. And then we do Gauss elimination. I will skip the process and get straight to the elimination. That's 0, 1, 2, 0, 0, 0. And since the third column is that of a free variable, free, I'm not sure if I told you the word free of unbounded.
You did.
You did.
Yeah, so a free variable, and the third vector is redundant. We don't know currently why, but that's the way we do it. Okay, the vectors that matches bounded variables are independent, and the rest you can strike out, they are unneeded. And we will learn why is that true later, but I'm showing you, like I said, the whole profile of the thing. Any questions so far? Now I just say that I also asked about the subspace W, which is a plane. The intersection of U and W would be a straight line in this case, which is also a subspace, which is one-dimensional. Okay, so these are the kind of questions we wish to answer. We wish to define accurately and then answer. Okay. So for now, what I will do is define subspace. So now definition. Given a vector space V over the field F, sorry, and given a subset U of V, we say U is a vector subspace. We use subspace for short. Is a subspace of V if it is a space, a vector space by itself with the same operations as V, meaning the 7 property holds for the same operations. You take U, a subset, you take the same addition, the same multiplying by a scalar, and if all 7 property holds, then it is considered to be a subspace. Okay, agreed? I'll give you a quick example. Take the set U of the first quarter of the plane, meaning both x and y are non-negative. This is an obvious subset of the plane. Just a second, sorry, I forgot to write. In which case we write U smaller or equal to W. So when the sign is round, it's a subset. We take this sign, it says a subspace. Okay. So
I know when we use the same symbols for different things.
yes. Also this, what is XY? So some would say a point in space, and some would say a segment on the real line. Yes, mathematician love to use the same notation for many different things. We even have a word for it, you know? What do you call it when we use the same notation for different things? Abuse of notation, which actually is abuse of the students, but the term is abuse of notation. Okay, so U, the first quadrant, is definitely a subspace of the plane because we take points in the plane. But the question is it a subspace? Is U not only a subset, but is it a subspace?
No.
Why?
Because you can use negative scalars and you get all of
Exactly. And what property does not hold? Let's look at it for a second. At the properties. Commutativity. I skipped in purpose. Does that hold? Yes. V plus W is still W plus V because the operation is the same operation. Associativity, same. Zero vector, that's a question. Does the quadrant have the zero vector?
yeah.
Yeah, 0, 0. Opposite vector. No, that's a problem already. It's not the one that you mentioned, but it's also a problem here. Unit scalar property, again, it's immediate. Distribution is immediate. So how much? Yeah, 4 of the 7 properties are immediate. 2, 3, 5, not 5, sorry. 2, 3, 6, and 7 are obvious to any subset. 1, the closure. 4, the zero vector. 5, the opposite vector. These 3 properties are not immediate. And what usually always makes something that is not a vector space, subspace, to be not a vector subspace. And in this case, we'll take the first, closure. So, and that's interesting as well. Do we have closure with addition? If you take 2 points, if you take 2 points, 2 vectors in the first quadrant, quarter of the plane, does the sum of 2 such vectors remain within the quadrant?
Yeah.
Yes, because if x, y are positive and a, b are positive, the sum is also 2 positive numbers. So it has closure with addition, but it does not have closure with scalar multiplication. No, it is not closed under scalar multiplication. 1, 2 is a vector in the set U, but -1 times 1, 2, which is -1, -2, is not a member of this set. So that is not a subspace. Example. How about U, which is all of the points x, x plus 1 within the plane. Is U a subspace of a plane?
Yeah. I think.
Yeah, proof, I think.
I'm pretty sure.
QED.
I'm pretty sure I saw it in a book.
Okay, that's an
Proof by reference.
yeah, no, yeah. But
You remember that?
it's not even I've seen it in a book. I'm pretty sure I've seen it in a book. Yes.
Proof by assumption.
Yeah. Assumption of reference. Yeah.
Proof by authority. They
Yeah.
have a pretty good
So
friend.
obviously the answer is not. It's not subspace. Okay. Even though Thomas is pretty sure he's seen it in a book. The book was called Big Book of False Statements. Okay.
What's wrong here?
Numerology. Okay. So why is it not a vector space? Look. consider 1, 2, which is within that set. Agreed? And also 2, 3. 2, 3. They are both vectors within that set. Agreed? Then who else should be in the set? By closure.
3, 5.
So there's some 3, 5 is not. It's not transitive. It's not a relation. It's I know. It's not like. It's it's some statement about things. No, being serious for a second, relations were with the question of no, but it was take two elements, you say do they given two elements, you say do they keep the relation or not? Like this is bigger than that or not? Operations are not relations, they are functions. Given two elements, you get a third one, right? So what would be transitive about it, right? You always take one element, add another element, and get a third one, right? But this so-called transitive question, no, there is a value. Because the question of whether the element is within the set is not a relation between two elements. It's just a property of an element, right? So yeah, I don't see any way to insert the transitive word here, other than Sammy said it's transitive and he was wrong. Okay, no.
Is that also in the big big book of false thing?
No, it's so sorry, we're over time, but it's so confusing really learning about maths using discrete mathematics eyes, because everything there looks the same, right? Everything is everything's are empty sets within empty sets within empty sets, and that's one way to look at mathematics, but it's sometimes confusing.
And life.
Yeah, it's life, yeah. Okay. My ex was an empty but an empty set, but I put her inside another set, and now, oh, sorry. In any case, 3, 5 is not here because the difference between the two coordinates is 2 and not 1. Therefore, U is not. Thank you. U is not a subspace. A subspace. Okay. So we did a lot today, basically. We learned a lot about vector space and subspaces, not a lot of theorems, but we learned a lot about what we actually need to understand about this material.
Don't we have another hour?
I know. No. Before we start calculus. Yeah. The time flies where you are
You're having fun with
suffering, yes. Okay. Thank you, everyone. See you on the next one, which is probably in half an hour. For most of you.
I thought we had 1 more hour, and I was like, this is pretty long.